Okay, hello everyone. I wanted to make a quick preview video on L'Hopital's rule. And this is looking at the 0 over 0 case, but there are other cases for L'Hopital's rule, in particular infinity over infinity, and even 0 times infinity are examples of cases where you can apply L'Hopital's rule. So let's look at what the theorem actually says. It says that if you have f and g are differentiable functions on an open interval containing the point a, except at possibly the point a itself, and you know that the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is 0, then the limit as x goes to a of f of x over g of x, so this quotient, is equal to the limit as x goes to a of f prime of x over g prime of x. And what's nice about that is that the derivatives f prime and g prime are typically easier to deal with. If it's a polynomial, you know you're getting something of lower degree, and I don't know. It just gives you a shot at evaluating this limit. Is what I want to say there. So you have to assume that the limit on the right exists, or is infinity or negative infinity. And again, it says this also holds if we're considering one-side limits, or even a equals infinity or negative infinity. So let's just take a quick look at this first couple examples. So this first one says that this is the limit as x goes to 1 of x squared minus 1 over sine of pi of x. And so x squared minus 1 is differentiable. Sine of pi of x is differentiable. We know how to take those two derivatives, so I think we're fine there. And then what happens if I actually evaluate at x equals 1? If I plug in 1 into the top, I get 0. And if I plug in 1 into the bottom, I get sine of pi, which is also 0. So this is one of those 0 over 0 forms. So that what we can do is we can apply L'Hopital's rule. So I always write LH over an equal sign if I'm applying L'Hopital's rule. And so I get that this is the limit as x goes to 1 of 2x over cosine of pi x times pi. I was just applying chain rule there. Okay, and so now 2x is certainly easier to deal with than x squared minus 1, and cosine pi x times pi is not really any worse than sine of pi of x, so let's evaluate now. Well, on the top I get 2, and on the bottom I get negative 1 times pi, so negative pi. And so that L'Hopital's rule says that that's the limit. And maybe we can just take a quick look at that graph to see that you believe what we just calculated. So here's the graph of x squared minus sine of pi x. And you can see that if you evaluate at 1, you get something that's undefined. If I drag my cursor over the graph at x equals 1, I get that it's undefined there. So there's a little hole there. But then if I plot y equals negative 2 over pi, you can see that that point actually fills in that hole. So this is the limit there. Okay, so let's go back and look at another example. And maybe one that isn't 0 over 0. So there's a little blurb in the textbook that says that we can do 0 over 0 and infinity over infinity. And then we can do all these other expressions like 0 times infinity, infinity minus infinity, 1 to the infinity, infinity to the 0, and 0 over 0. Those are all what are known as indeterminate forms. And the trick for this is you really just try to turn it into either the 0 over 0, infinity over infinity case by doing a little bit of algebra. So the limit as x goes to 0 from the right of x ln of x, that would be a 0 times a negative infinity case. And so what we're going to do is we're going to turn that into a 0 over 0 case, or an infinity over infinity case, by just doing a little algebraic trick. So this is going to be the same as the limit as x goes to 0 from the right of, and I'm going to write this as natural log of x divided by 1 over x. And so if you're struggling to see how we got from here to here, all I did was multiply top and bottom by 1 over x. And so that canceled, that's just a 1 there, and I get the same thing. So these are exactly the same expressions. But now both of these are differentiable functions, and if I plug in 0, I get negative infinity in the top, and I get infinity on the bottom. So now we have the indeterminate form, infinity over infinity, that we're used to dealing with. So L'Hopital's rule tells us that we should take the derivative of top and bottom, and we will get that this is the limit as x goes to 0 from the right of what? That looks like 1 over x divided by 1 over x squared, negative 1 over x squared, I should say. And so that simplifies down to the limit as x goes to 0 from the right of negative 1 over 1 over x. Does that seem right? Yeah, I want to say that that's just x, right? I could multiply top and bottom by x squared, and that would just give me x. Yeah, so this is the limit as x goes to 0 from the right of just negative x. And that is going to give us a 0. Okay? So if we plot that function in Desmos, close to 0, it should look like something like negative x there coming in there. So yeah, it has the same limit as negative x as x approaches 0. So we're good there. Okay. And now I wanted to do one more example. The last example I want to do is natural log of x over cotangent of x. So this is example number 3. Calculate the limit as x goes to 0 from the right of natural log of x over cotangent of x. And I want you to just kind of pause the video and think about what indeterminate form that is. And you should get something like negative infinity over maybe negative infinity. So it's an indeterminate form of the form infinity over infinity, so we can apply L'Hopital's rule. Of course, cotangent of x and natural log of x are differentiable. We're going to take the derivative of them in a second. So this is equal to the limit as x goes to 0 from the right of 1 over x divided by cosecant squared x, and negative cosecant squared x. Okay, well, what's negative cosecant squared x? That's, cosecant of x is 1 over sine. So this would be negative 1 over sine squared. So I think that this expression is the same thing as multiplying both top and bottom by sine squared. So I think I'm going to get that this is the limit as x goes to 0 from the right of negative sine squared x over x. And now if I try to plug in 0 there, I get another indeterminate form. I get 0 over 0. So I'm not done yet. But the nice thing about L'Hopital's rule is we can apply it several times. Okay, so because I had 0 over 0, I can take the derivative again of the top and the bottom. And this time I get the limit as x goes to 0 from the right of, what is that, negative 2 sine of x times cosine of x all over 1. And again, taking the derivative of x made things much nicer because now I don't have a ratio anymore. I just have negative 2 sine of x cosine of x, and I'm evaluating it to 0. When I evaluate it 0, I think I get 0 times 1. So I think I get that this is 0. Negative 2 times 0 times 1. So let's take a look at that graph on Desmos to finish up this video. So let's see, I think I had that plotted right here. And you can see that while you get negative infinity over negative infinity, when you apply L'Hopital's rule, you do get that the limit is 0. And you can see that that's clearly the limit from the right of this function. Okay, thank you for your time. Have a great day.